All right, here we go. We are in section 3.2 from the book, and this is, we go full screen. The title of the section is called Solve Linear Systems Algebraically. You have, I'm sure you've done this at some point. So it's nice review, but let's go through it and take it on as if in case it was a new subject for you. So we have two ways to solve linear systems, either substitution method or the elimination method. Vocabulary-wise, substitution method is substitute an expression into one of the equations to solve for the variable. An elimination method, and some people also call this the addition method, but we eliminate one of the variables by adding equations. Again, by adding equations. Maybe that's why some people call it the addition method. Substitution method. Here are the steps. Step one is to solve one of the equations for one of the variables. So you have basically a choice of four possible ways to start a substitution method. Substitute the expression from step one. Let's just write step one into the other equation and solve for the other variable. Step three is to substitute the value from step 2 into the revised equation from step 1. Kind of wordy. I think we need an example. And here we go. So here are your two equations, right? Both lines presented in standard form. It says solve the system using the substitution method, equation 1 and equation 2. So we should talk about planning here. You've got two different equations and you can solve either one of them for one of the variables. Hopefully you're seeing right away that with the first equation, the fact that there's nothing in front of the x variable, which means there's a 1, that's the equation to solve for x. Again, you could solve the same equation for y, but then you're dealing with fractions, and we prefer not to. And again, you could solve equation 2 for either x or y, but then we're again dealing with fractions, and we prefer not to. So if we solve equation 1 for x, we will get negative 2y minus 2. And then we take that equation and substitute it into the second equation for x. So instead of writing 3x plus 4y, we now write 3. Again, x is equal to negative 2y minus 2 from the first equation. And now we're excited, right? And algebraically, I have one equation, one variable, the y variable, and I can solve for it. So you'd have to distribute the 3, combine like terms, and finally solve for y. And looking here at my notes, that's y is equal to negative 6. So again, you probably would take a few steps to do this. I think the book is saving a little space and just solve for you. So what do we do? Well, we have half the answer, right? We know that the y value of the solution is negative 6. We need the x value. Again, you have choices to make here. You could plug into either equation. Notice that the first equation, you already solved for x, so it's probably the fastest move and the least amount of steps for you is to plug into that revised equation. So put the y value, or set the y value to negative 6 and solve. And now I guess they're giving us a little bit of room here to solve this. So this is 12 minus 2, and this would be 10. And so your answer is 10, negative 6. Again, yesterday in class we did, or today in class I should say, depending on when you're watching this video, we solved using the graphing calculator to find an answer, and this is another method, the substitution method. So we also have the elimination method. So elimination method, typically we do this if we can't use the substitution method. So we multiply one or both of the equations, and we'll give you an example of each case, either one or both equation, by a constant. To obtain coefficients, again, coefficients are the numbers in front of variables that differ only by the sign of one of the variables. And we'll show you what that means in an example. Step 2 is to add the revised equation. So again, that's why some people call this the addition method. So from step 1, combining like terms will eliminate, and that's probably why they call it the elimination method. Sorry. one of the variables and solve the remaining variables. You do substitute the value obtained in step 2 into either, again, either. You have a lot of choices to make when you do this type of algebraic solution. Either of the original equations to solve for the other variable. Well, let's do an example. So here we go, kind of lengthy here. Here are two equations, and notice right away that both equations, there are constants in front of x and y. So again, using substitution method here, would be a little trickier. We probably would get fractions. So what we end up doing is saying, all right, let's do the elimination method, or sometimes you're just told you have to use the elimination method. So looking here, it looks like if I multiply the first equation by -2, then I'll have coefficients of -4 and 4, and we'll have an elimination. So we're going to multiply here by -2, and this first equation, again, multiplied by -2 will give us -4x minus 10y is equal to -28. Oops, I have a hard time writing here. 8. There we go. And finally, the other equation was just as is, so let's just rewrite it. Good housekeeping here. And so when I add these two equations together, notice the -4 and the +4 are going to cancel, and that's successful elimination method. -10y plus 2y is -8y. This would be -24. Divide by -8, and my solution is 3 for y. So again, I'm halfway there. My solution is 3. I need to still figure out what x is, so what do I do with the y equal to 3? I can plug into either of the two equations. Looks like the book just picked the first one. There's really no difference. Both equations will work. You'll get the same value. And it looks like x solves for -3. And there's your solution. Now, look at this excellent little check here. You actually have two ways to check. The first way would be to plug -3 into into both equations, excuse me, and see that they satisfy, right? -6 plus 15 is 14, that works. -12 plus 6 is -4. So you could simply plug in and check it out. They say, look, you can always use your graphing calculator. Again, if you have the time and you're allowed to use your calculator, why not plug into the calculator and have a check? Speaking of check, why don't you check and see how things are going? If you want to hit pause, and it says, here you have to solve the first one using substitution method and the second by elimination. Go ahead and hit pause, and when you've got answers and want to check, go ahead and hit play. And there are the two answers. So I'm going to keep going. Again, people could have solved this different ways, and if you didn't get one of these two answers, I would highly recommend checking and seeing where your mistake was, and if you're not able to do that, ask me tomorrow in class. So I'm going to move on to another example of elimination method. I'm actually giving you the key here just to kind of speed things up. The reason for this example is that you can notice that, with the two equations given, it's not apparent like, the last time we just had to multiply one equation by a constant, but here it's clear we need to multiply both equations. So the first equation is being multiplied by 5 to get the 15x, and the second equation is being multiplied by 3 to get this -15x. So the goal here was to eliminate the x variable. Again, you might have looked at this equation and said, hey, I'm going to eliminate y by multiplying the first equation by 3 and the second equation by 4. And that would have worked just as well. So once you've done that, and that makes the elimination method a tricky method, but very doable. You solve for y, and then all the steps stay the same. You plug 13 in, you get your x, and you're welcome to check. So here's an example, and it's a good one, where you're solving a linear system that have either many solutions, or what we'd said today in class, infinite solutions, or no solutions. And again, no solutions would be two parallel lines. Infinite solution ends up being the same line. So here are the two examples. Example A, two different equations given to you. When you go to solve, what ends up happening is the book here is using the substitution method. When they substitute in, they solve the first equation for x, substitute into the second equation, and then as they start going, notice this 2 distributed into 3y gets you 6y minus 6y. The variable y cancels. And all you're left with is 14 is equal to 12. And by the way, that is not equal, right? 14 does not equal 12. So it's never true. And then what you need to do is take it and say, hey, there is no solution, right? These lines ended up being parallel. And you might have noticed that a little bit by looking at the equations. If you were to graph them, they would be parallel lines. Our second example here is in the case where there are infinitely many solutions. So this is, we're now looking at the second example here, the two equations given. Here, both equations are multiplied. The first equation by 5, the second equation by 2. You can see the buildup here, and we're going to cancel, but notice everything cancels. But we're left with an equation that is true. 0 is equal to 0. And again, let me scroll back. The last equation, we eliminated the variables, but we're left with an equation that makes no sense. 14 does not equal 12, so that there is no solution. But notice when your variables cancel and you're left with an equation that is true, but your variables are gone, then we say that there are infinitely many solutions. Hope that makes sense. Why don't you go ahead and do 2 more problems just to see how it goes? Go ahead and hit pause, and when you're ready, hit play. And we're back. So problem 3, there actually is no solution. These are 2 parallel lines, and you should have eliminated both variables and come up with an equation that didn't make sense. And then here, the second one looks like you could either have eliminated x by multiplying the first equation by 5 and the second equation by -2, or you could have eliminated the y's by multiplying the first equation by 7 and the second equation by -3. Hey, we'll see you tomorrow in class. Thanks.